Happy learning! Today we're going to talk about the Gauss-Jordan Elimination method, which is used for solving systems of equations. Okay, so we'll start really by just jumping right into what the Gauss-Jordan Elimination method is. So suppose we want to solve the system of equations given by 2x plus 5y plus 4z equals 4, x plus 4y plus 3z equals 1, and x minus 3y minus 2z equals 5. All right, one method we could use is write out the coefficient matrix and find its inverse, and then multiply both sides of some equation by that inverse. But it's possible that the coefficient matrix doesn't have an inverse. Not every matrix has an inverse. So this method that we're going to talk about today will deal with how to solve any system of equations, not just ones where the coefficient matrix has an inverse. All right, so we're going to use what's known as the Gauss-Jordan Elimination method. Okay, so we're not going to be using the system of equations. We're actually going to be using an augmented matrix. So instead of having all of the variables and the plus signs, we're going to just list out the coefficients, and then we'll have a vertical line to represent the equal sign. So we're going to be dealing with this matrix. All right, how did I get this? I just read off the coefficients, and then the equal sign is going to be represented with this vertical bar. Okay, so the first step in the Gauss-Jordan elimination, we need to get a 1 in row 1, column 1. We're allowed to use the elementary row operations. So we can swap rows, we could add multiples of one row to another, or we could scale a row. Right? So those are our 3 steps we're allowed to do. So in our example, we could do this a number of ways, but swapping rows 1 and 2 seems to be the most natural. All right, so this gives us a new augmented matrix. All right, the next step is add multiples of row 1 to other rows. To get zeros in the first column. All right, so what can we do here? We're going to add -2 row 1 to row 2 and negative row 1 to row 3. All right, so row 2 will become row 2 minus 2 row 1, and row 3 will become row 3 minus row 1. So row 1 stays the same. And row 2, 2 minus 2 is 0. 5 minus 8 is -3. 4 minus 6 is -2. And 4 minus 2 is 2. For the bottom row, 1 minus 1 is 0. Negative 3 minus 4 is negative 7. Negative 2 minus 3 is negative 5. And 5 minus 1 is 4. Okay, so now we're going to, so the next step, step 3, we're going to use the rows below 1 so we're not going to touch row 1. So we're going to either use 2 or 3, but I mean this works for bigger matrices as well. So use rows below row 1 to get a 1 in row 2, column 2. So there's a number of ways we could do this. Right? We could double row 2 and then subtract off row 3. That would work. The simplest way is I'm just going to scale it. All right, so row 2 will become negative 1/3 row 2. I know we're going to introduce some fractions, but I have faith in you. You could deal with fractions. You've been doing it since 4th grade. So be comfortable with fractions. All right, so our top row stays the same. Our second row is scaled by this factor of negative 1/3. And our bottom row stays the same. Okay, what's the next step? We're going to add multiples of row 2 to the other rows to get zeros in the second column. All right, so we're going to add negative 4 copies of row 2 to row 1 and 7 copies of row 2 to row 3. So row 1 will become row 1 minus 4 row 2, and row 3 will become row 3 plus 7 row 2. All right, and so when we do this, we get the following. And now we're going to kind of repeat this process. Now dealing with only the last row, we want this to become a 1. And then we're going to add multiples to the top rows. All right, so let's scale this. So row 3 becomes 3 row 3. So top 2 rows stay the same. And the bottom row, we're scaling by a factor of 3. All right, and then we're going to use this 1 in our bottom row, or in our third column, to turn those to zeros. All right, so row 1 will become row 1 minus 1/3 row 3. And row 2 will become row 2 minus 2/3 row 3. And when we do this, what we get is this. Okay? this is what we call in reduced row echelon form. We can't do any more steps. We got our identity on the left. Now what we're going to do is each of these rows corresponds to an equation. This top row corresponds to the equation x plus 0y plus 0z equals 3. 0x plus y plus 0z equals minus 2. And 0x plus 0y plus z is 2. The reason why I was reading out those equations is there's going to be times where it's not going to be perfectly clean like this. And we might have something known as a free variable. And so there could be infinitely many solutions. So we do have to be careful. OK, so this process is a little bit of a pain. So it could be done with a TI-84 calculator. So the way you do that is you go to Second, Matrix, Math, and then you select B, which is for RREF. And that will turn our augmented matrix into this reduced matrix. OK, let's take a look at an example. And I'm not going to go through and do all the row reduction. So I'm going to write out maybe a system of equations, and then I'm going to just write down what the final step would be, because we're going to say that we did it with a calculator. All right, so suppose we have the following system. We're going to have 4 equations and 4 unknowns. So x plus y minus z plus w equals 3. Y plus z plus w equals 1. X minus 2z plus w equals 6. And 2x minus y minus 5z minus 3w equals minus 5. All right, so we have 4 equations and 4 unknowns. And we want to solve this system of equations. And so what we could do is let's write out our augmented matrix. And then we could use Gauss-Jordan elimination, or just have the calculator do it, to row reduce our matrix. All right, so what is our augmented matrix going to look like? Remember, we just read off the coefficients. So it's going to be, the top row will be 1, 1, minus 1, 1, and then a 3. The next row is 0, 1, 1, 1, 1. One, 0, minus 2, 1, 6. And 2, minus 1, minus 5, minus 3, minus 5. OK, we then use our calculator to put it into RREF. This is called reduced row echelon form. Basically, it does all of our row operations. And we get the following. 1, 0, 0, 0. 0, 1, 0, 0, minus 2, 1, 0, 0, 0, 0, 1, 0, 2, minus 3, 4, 0. OK, and so this is as we would be done with doing our row operations. We want to solve the system of equations. And so what we're going to do is translate each of these rows back into an equation. This says x minus 2z equals 2. right? 1x, 0y, minus 2z, 0w equals 2. The next row, 0x, y plus z equals minus 3. This next row says that w equals 4. And the final row says 0, right? 0x plus 0y plus 0z plus 0w equals 0. That's giving us no new information. And so what we're going to do is we're going to solve for the leading variables. Leading meaning showing up more left in our matrix. All right, so we're going to solve for x in terms of z, solve for y in terms of z. So we have x equals 2z plus 2. Y equals minus z minus 3. W has to be 4. And we have no way to solve for z. So z is called a free variable, or it could be any number. So each value of z gives us a different solution. There's infinitely many solutions to this system. Right? If z was 0, then x would be 2, y would be negative 3, and w would be 4. If z was 1, that gives us a different solution. 4, minus 4, 1, and 4. Okay, so there's infinitely many solutions. All right, so each value gives a new solution, so there's infinitely many. Let's take a look at another example. Solve the system. So we have x plus 2y minus z equals 3. 3x plus y equals 4. And 2x minus y plus z equals 2. All right, so just like we did in the last example, let's turn this into an augmented matrix. We'll do our row operations, or have a calculator do it for us. And then we'll see what our solution is. All right, when we do our row operations, we get 1, 0, 0, 0, 1, 0, 1/5, minus 3/5, 0, and 1, 1, 1. Okay, and so what happens? Let's write out our equations. This top row says that x plus 1/5 z equals 1. Okay, so far so good. Y plus 1/5 z equals 1. I was lying. Y minus 3/5 z. I was testing you all. Equals 1. And then the last equation says 0x plus 0y plus 0z equals 1. The last equation says 0 equals 1. This is total and complete nonsense. Right? 0 does not equal 1. So this equation here, 0 equals 1, if you want to call it an equation, this is inconsistent. There is no solution. This is saying in order for a solution to exist, we would need 0 to equal 1, which it doesn't. Okay, so if when you do your row operations and you get an equation that says 0 equals something that is not 0, we're going to be in the case when there's no solution. All right, let's look at one application. A trust account manager has $500,000 to be invested in 3 different accounts. The accounts pay annual interest rates of 8%, 10%, and 14%. All right, we have these 3 accounts, 3 different interest rates, various levels of risk associated with them, and the goal is to earn $49,000. So we want to split up this $500,000 into these 3 accounts, earn some interest, and that interest, the amount we earn, is $49,000. The question is, how much should be invested in each account? All right, I know this might look intimidating, but I have faith in you. Let's write out a system of equations that needs to be solved, and then we could use our techniques from today to solve this system. All right, so there's 3 different accounts. I'm going to call them X, Y, and Z. And so the amount invested in X plus the amount invested in Y plus the amount invested in Z has to be $500,000. The amount invested in X gets 8% interest. So 0.8X plus Y gets 10%. 0.1Y plus 0.14Z equals $49,000. All right, and that's it. So now let's write out an augmented matrix, and we'll do the row operations. Our augmented matrix is 1, 1, 1, 500,000, and 0.08, 0.1, 0.14, 49,000. All right, we would do our row operations. So put it into RREF. And we get the following: 1, 0, 0, 1, minus 2, 3, 50,000, 450,000. Let's write each of these as an equation. This top row says that x minus 2z has to be 50,000. The next row says y plus 3z equals 450,000. There's no inconsistencies here, right? We don't have a 0 equals 1, so that's great. That's saying it is possible to find a solution. And so we don't have an equation for each of the variables. So there's going to be infinitely many solutions. So what do? We want to get the leading variables in terms of the later in the matrix variables. So let's solve for x in terms of z. We'll solve for y in terms of z. This gives us that x is 2z plus 50,000. And y is minus 3z plus 450,000. And z can be anything. Okay, there are probably some constraints, right? We want these values to be positive or non-negative at least. But what we could do is just say, all right, we're not going to put any in z. That means we're going to put $50,000 in x and then the remaining $450,000 in y. Okay, so one example solution. There's infinitely many solutions. So one example could be x equals 50,000, y is 450,000, and z equals 0. Maybe this z is the riskiest one because it has the highest return, so it probably is the riskiest. So maybe you don't want to risk it. Okay? And so, yeah, what's the takeaway? These tools are useful not just for solving just systems of equations, but word problems that could be restated as systems of equations. All right, well, I hope you found this video interesting, and let me know in the comments if you have any questions or concerns. All right, see you later.